second session of today, a topic very dear to my heart, succinct proofs. So we have 5 talks today in the session, and the first one is on black box. This is complexity preserving sublinear arguments, and Rishab Badora will give the talk. Yeah, go ahead.
Yeah. Hi, I'm Rishab, and today I'm going to present our work, Complexity Preserving Sublinear Arguments from Symmetric Key Primitives. And this is a joint work with my great co-authors, Lasya, Mathu, and Karmeet. So let's start. We first talk about zero-knowledge arguments. So again, there's a prover, and the prover wants to prove to the verifier that a given statement is a part of it belongs to a language. And here, we get all the standard properties, which is completeness, soundness, and zero knowledge. But additionally, we also want the zero knowledge argument to be succinct. So here we want the communication or the proof size to be polylogarithmic in the statement size and in the security parameter. So our main question here, or the main question which we are trying to investigate in this work, is can we construct a complexity preserving public coin succinct argument from minimal assumptions? And the answer is yes. So first, what is complexity preserving, right? It basically means that the prover's complexity has a minimal or no overhead compared to verifying a NP statement in a standard way. So here we want a proof size to be succinct. We want it to be non-interactive. We want no trusted setup or a transparent setup. We want to achieve zero knowledge, as well as we want only symmetric key crypto. Oh, sorry. Here we get the proof size to be succinct, but it's sublinear. So here there's a whole lot of work on snarks and ZK snarks, as you can see here. And basically here we model our NP statement as a uniform RAM program that takes time t and space s to verify an NP statement. And here we want the properties like succinctness. We want it to be public coin or public verifiable. We want complexity preserving, such as time and space preserving. And we want it to be black box in the underlying assumption. And there are many works which actually get a strict subset of these properties, but not all of them. So for example, there's some works which get which use private coin or not publicly verifiable. There's some works which requires the space complexity to be proportional to the running time t. There's some works which are either non-black box in the underlying assumptions, or they use a heuristic assumption. Or there's some works where if you constrict the space complexity, the running complexity blows up. And here Block et al. Proposed 2 works which actually satisfy all of these properties, but they are based on number theoretic assumptions. The first paper is based on discrete log, and the second is on hidden order groups. And the question we ask in this work is, can we get something based on symmetric key primitives? So here our model is RAM program, and here you have a RAM machine, and the prover and verifier is modeled as one RAM machine. And basically you have 2 tapes. One is the input tape and the work tape. The input tape, the RAM program just has a linear axis, while the work tape, it has a RAM axis, and the space complexity is equal to the size of the work tape. So here our first result is, assuming that collision resistant hash function is used as a black box, we construct a public coin zero knowledge argument with negligible soundness for NP languages that can be verified using a RAM machine running in time t and space s. And here we get the prover's complexity to be complexity preserving. That means the running time is t and space is s. And we get the verifier's complexity and proof size to be sublinear. So now here, if here now you set the space s to be square root of the running time, here you can get the time and proof to be square root, which is sublinear. And here in all these complexities, we just ignore polylog t kappa factor. And our second result is that we actually show that to reduce the proof size further, it's hard based on current techniques. And let's start with our protocol is based on Ligero. So let's start with an outline of Ligero. So here, given a circuit C, we want the prover wants to prove that it knows a witness Z such that it satisfies the circuit. And here you have the prover evaluates the circuit at the extended witness Z, and now it will generate an extended witness, right? So the extended witness consists of the intermediate wire values, and it consists of the input wire values and the output wire values. And now, sorry, yeah, now it will arrange all. Oops. Sorry, guys. Yeah. Now it will just arrange it in a matrix of size A cross B. And now what you do is you encode each row of this extended witness using a Reed-Solomon code or any other linear code. And now basically you can divide the protocol into 3 phases. The first phase, please work, computing the Merkle tree, wherein first the proof oracle, which is generated by encoding the extended witness, you commit to it using a Merkle tree. The second phase is you generate a row aggregate. In this step, the verifier sends some challenges, and the prover using these challenges will generate a row aggregate, which is by taking a function of these challenges and the proof oracle and combining them together. And the third phase, the third phase is decommitting to the columns, wherein the verifier will ask some queries on the proof oracle, and the prover will just open these columns and give authenticated pass to verify. And here the proof size is equal to B plus kappa I. So here B is the size of each row, and A is the size of each column, and kappa, or the security parameter K, is the number of columns you have opened. And now if you set the number of rows to be space S, then you get the proof length. Sorry. Here you get the proof length to be T. Here you get the proof length to be T by S plus S, and you get the prover's computation to be order T, which is in sync with our result. So, okay, now we talked about running time, we talked about the proof length. Now what about space efficiency? And so here, we want to compute computing the Merkle root and decommitting the columns can be easily made, can be done in spaces if the matrix can be computed, the extended witness can be computed row by row. And for that, what we do is, Ben-Setson et al. Gave a transformation from RAM program to a succinct circuit. And using this succinct circuit, we can basically generate the transcript or the extended witness in time t and in space S. So now the second step is how actually do we generate the Merkle tree in space S, right? So what do is you read each row of the extended witness, you encode it, and then you apply a hash on it. So you use some, you actually use a running hash, which you can implement using a Merkle-Damgard hash function. And then you again, you read another row, you again encode it, hash it together. And at the end you will get a, after processing all the rows, you will get hash or a commitment for each of the columns. And now this will require only spaces. And now you can just apply a Merkle, Merkle commitment on it. And so now you can basically compute the Merkle tree commitment just using order spaces instead of order T. So now what about the row aggregate? What about the space efficiency of this? So now basically the row aggregate is generated by first by generating the proof oracle, and then you apply a function on each of the rows and you aggregate them together. And based on our different tests, we have a different row aggregate for each of them. And now again, the tests are based on, first you want to verify whether the encoding was done correctly, and then you want to check whether the multiplication and linear gates were done correctly. So here we're just going to focus on the linear test. So here you can express all linear, like in general, you can express linear constraints as a linear expression, and you can express it as AW equal to B. So A here is the linear constraint matrix, B is the linear constraint vector, and here W is the external witness. And now what the test is that the verifier will send a random vector or a challenge to the prover, and the prover will compute an encoding of RTAW. And now the verifier will just check whether the encoding Q is a valid code word encoding RTB, and it agrees on the proof. It agrees on the columns of the proof oracle. Okay, yeah. And the main challenge is how do you compute RTA efficiently? Because the size of RTA is number of constraints into the number of wire values, which is order T cross T, and the size of R is only order T. So again, even if you want to naively multiply, you would require order T square space and order T square time. So a very simple thing which you can do is instead of generating generating R directly, you can generate R using a seed, and that would require only constant amount of space. What about matrix A? So here, if we have A to be a sparse and structured matrix, it works out. So now Ben-Sisson et al. Transformation, which we used before, converts a uniform RAM machine into succinct circuit, and you get a succinct matrix out of it. So the linear matrix will be succinct. So now you can compute all the non-zero values in a column in constant time without actually storing the A matrix at all. And so now you can compute RTA row by row in time T and space S. And therefore the overall complexity of the prover is complexity preserving. So now basically we move on to our lower bound. I just want to say some words about that as well. So our lower bound, basically we show that based on current techniques in the symmetric key, it's hard to improve the proof length further by T by S. And the basic I don't know why it's going there. Okay, so what you do is you take a RAM program, you convert it into a transcript, and then you convert that you encode this transcript, right? And now basically you encode this transcript using constant distance codes, and therefore if you show we show that there's a lower bound on the constant distance code, and based on that, because of that, to improve the lower bound in symmetric key operations is difficult. And so again, we show that for a given any R-pass encode RAM algorithm, which takes in n symbols, outputs a code of m symbols, and has a distance of delta m, the space required is delta n by R into log f, where delta is the distance factor. And now we prove that Ben Yosef in 2002 et al. In 2002 proved the lower bound for a single pass algorithm. We show it for a R-pass algorithm, and now for complex, because we want a prover to be complexity preserving, we set n equal to t, and we get delta as SR by T log T. And because the proof size is based on the number of minimum oracle queries, we get the lower bound as T by S. So, sorry, last slide. In summary, we give the first construction of complexity preserving sublinear zero knowledge argument from collision resistant hash function in a black box way. And we show that improving the communication will just require new techniques, which is actually getting around the constant distance code. Thank you.
Thanks, Rishabh. Any questions? We need time for a quick one while the next speaker sets up. Other Rishabh.
So maybe a quick clarification. Is the lower bound dependent upon anybody using a technique that relies on a code for encoding each row? I mean, if hypothetically use something else, then.
So our technique requires that you use the transcript and convert, you encode the whole transcript. using a constant distance code.
But you encode each row of the transcript using a different code, right? Or
Yeah, I mean, that's our upper
Yeah, yeah.
bound. But when we are talking about the lower bound, we actually encode the whole.
the whole thing. Okay,
Yeah.
got it. Thanks.
Great. Let's thank Rishabh again. So the next speaker is Gal Anon from Weizmann, who's going to tell us about barriers for interactive Oracle proofs.
Okay, so I'll be talking about a toolbox for barriers on interactive Oracle proofs, and this is joint work with Ame, Alessandro, and Delon. So in a PCP system, we have a verifier who wants to know the validity of some statement. A prover sends it some string. Verifier reads a few symbols from this proof and decides whether to accept or reject the statement based on this information. In PCPs, we usually care about the length of the PCP, the alphabet size, the number of queries made by the verifier, the soundness error, and sometimes also things like completeness error and the number of random coins used by the verifier. So let's take a look at some things that are known for PCPs. So first of all, we have the celebrated PCP theorem, which says that NP has a polynomial length PCP with constant alphabet size, constant number of queries, and constant soundness error. But we computer scientists, we're greedy. We see this amazing result, and we say, I want to improve this. So one way to improve it would be proving the length, this polynomial length to linear length. And this is a great open question in PCP literature. Another way to improve this PCP theorem would be to get the soundness error down from a constant to 1 over n. We can even allow the alphabet size to grow, but we want inverse polynomial soundness. And this is known as a sliding scale PCP, or the sliding scale PCP in the inverse polynomial soundness error regime. We don't know how to do this as well. What we do know is to get relatively close by work of Dinur, Harsha, and Kindler, which gets to polylog log n queries and this soundness error that we wanted. And finally, what if we really restrict the alphabet size and restrict the number of queries? Then for binary alphabet constant query PCPs, if we have just 2 queries, we know that there can't be PCPs like this. And if we have 3 queries, there can't be PCPs like this with soundness error that is better than 5/8. So now I'll introduce a generalization of PCPs known as IOPs, or interactive Oracle proofs. Here we have a interactive proof between the verifier and the prover. The verifier sends a message, the prover sends a message back, and so on. And at the end, the verifier reads a few symbols from each of the prover's messages and decides whether to accept or reject based on that. The parameters of interest for IOPs are basically the same, except that we also care about the number of rounds, since there's interaction now. So why do we care about IOPs? Well, IOPs have been really useful to get succinct arguments, succinct zero knowledge proofs, delegation of computation, and other results. So since they're a generalization of PCPs, one could ask, are IOPs going to help us with these things that we either don't know how to do for PCPs or we know are impossible for PCPs? And for linear length, actually, we know that it is possible. So we have IOPs with linear length, even though we don't know how to do this for PCPs. So this interaction really buys us something in this regime. And the question is, does this help us? Does interaction help us for these other results? And this leads us to our results. So we develop a toolbox for deriving barriers of IOPs. And using this toolbox, we show a bunch of results. The first is showing that sliding scale IOPs are essentially equivalent to sliding scale PCPs, showing limitations of binary alphabet constant query IOPs, and showing limitations of short IOPs. So I'll go through these one by one, starting with sliding scale IOPs. So we show a transformation from a sliding scale IOP with polylog n rounds to sliding scale PCPs. And this can be viewed either as a negative or as a positive result. On the negative end, it's a barrier to constructing sliding scale IOPs. So, constructing sliding scale PCPs is an open question. It's been really difficult. We haven't gotten, we don't seem very close to it. And so this basically tells us that it's going to be hard to construct sliding scale IOPs. On the other hand, maybe if we want to get sliding scale PCPs, this tells us that we can use interaction while trying to construct this. So if we go back to our table here, so we don't know how to answer this question for the sliding scale conjecture row, but we do know that these two question marks, whether it's possible for PCPs or possible for IOPs, are essentially equivalent. So going back to our results, and I'll go now to limitations of binary alphabet constant query IOPs. So as I said before, there are no binary PCPs for NP with either 2 queries or 3 queries and soundness error that is better than 5/8. And what about IOPs? Will IOPs help us here? Will interaction help us? Well, not really. There's no polylog n round binary IOPs for NP with 2 queries and soundness error that's very close to 1, or 3 queries and soundness error that's very close to 5/8. So other than this, very close thing, the takeaway is that in this regime, interaction is not really going to bias anything. So going back to our table, as long as we add this small thing that maybe IOPs can help you with, we still know that binary alphabet constant query IOPs, we can't construct them. So finally, let's look at limitations of short IOPs. So we show that there's no short IOPs in the DHK parameter regime. To remind you, the DHK PCP has polynomial length and polylog log n queries and inverse polynomial soundness error. And we show that even if you have polylog n rounds, you can't get this length down to like n times polylog n. And the full theorem considers a much more general trade-off between parameters. So other than these 3 results, we also have additional barriers that are related to interactive proofs, which I won't present in this talk. You can look at the paper if you want, if you're interested in that. So I mentioned that all of these results are developed using a toolbox that we built. What is this toolbox? Well, it's comprised of 3 main parts: round and length reduction, transformations for improving completeness, and transformations for de-randomizing IOPs. And the way we use them is basically, we pick and choose each one of these tools in a different order for achieving each of these results. And we'll look at the first one, showing that sliding scale IOPs are essentially equivalent to sliding scale PCPs. Okay, so just to recall, what are we trying to prove? We have an IOP with polylog n rounds, inverse polynomial soundness error, constant queries, polynomial alphabet size, polynomial length. And we want to turn it into a PCP, which basically means just reducing the rounds to 0. So we start off with an IOP. We want to get to a PCP. Where do we start? Well, a natural place to start would be to unroll the IOP into a PCP, by which I mean write the entire interaction tree of the IOP in a single PCP message. And this really does bring us down from polylog n rounds to 0. But the problem is that the length will be exponential in the number of rounds, which is polylog, and in the randomness complexity, which might be polynomial. And so this PCP would have exponential length, and we want polynomial length. So our goal now is to reduce the number of rounds and to reduce the randomness complexity. In order to reduce the number of rounds, we'll add a round reduction transformation, taking the rounds down from polylog n to a constant. And this is basically based on the fact that if the verifier has very few queries, it's not going to read most of the rounds. And so we might as well throw out the rounds that the verifier is not going to read. And that sort of allows us to compress the number of rounds. And then we'll add a de-randomization step to get down from polynomial randomness complexity to O of log n randomness complexity. And this is very similar to de-randomization of interactive proofs. Basically, the verifier samples its randomness from a subset of the random coins, either given to it as non-uniform advice or from some Nissan-Wigderson style PRG. And then it looks like we're done, right? We've managed to get the rounds down to a constant, the randomness to O of log n. And so this unrolling step now has polynomial length. But unfortunately, this round reduction degrades completeness from perfectly complete IOP to one that has completeness error 1 minus 1 over polylog n. So actually, the full view, we should also look at this column of completeness error. And this means that we want to go back to perfect completeness. So we'll add a step for going back to perfect completeness. And this is based on standard transformations to get perfect completeness for IPs, except that we have to take some care not to harm the query complexity. Not to harm the query complexity. And now we really are done. So we take the IOP, we reduce the number of rounds, we reduce the randomness complexity, we get back perfect completeness, and finally we unroll it into a PCP. And I will just mention that the order of the steps here does really matter. For example, this perfect completeness step increases the alphabet size as a factor of the randomness complexity. And so we have to put this after de-randomization. We can't just put it right after round reduction. So some thought has to be put into the order of these things. So just as a summary, so we developed a toolbox for deriving barriers for our IOPs. We showed that sliding scale IOPs are essentially equivalent to sliding scale PCPs. We showed limitations of binary alphabet constant query IOPs and limitations of short IOPs. And just as a general question raised by this paper and other papers, when are IOPs more powerful than PCPs? When does interaction really give you more power? It's just a good general question. All right, thank you.
Thanks, Gal. Are there any questions? Okay, then I have one. So all of these results are for polylog rounds. So what do we know about like more rounds? Do these questions make sense when you have more rounds?
So for some of these, for especially 2 and 3, the limitations of binary alphabet, constant query, and limitations of short IOPs, the actual theorems are more general. So they do say something for more rounds. For the sliding scale, I mean, it is more general, but it doesn't really work for polynomial number of rounds. So there could be hope of constructing a sliding scale IOP with a polynomial number of rounds, and this work doesn't say anything about it implying anything about PCPs, which would be a really interesting question, I think.
I guess where does the technique break down when you have polynomially many rounds? Is the round reduction doesn't work, or? Yeah,
the round reduction, basically you guess which rounds are going to be read, and once you even if you start with like inverse polynomial soundness error, once you you guess which rounds are going to be read, and then all the other rounds are thrown out. And if you guess wrong, then this is basically thrown out. And so you're going to lose, if you start with like polynomial number of rounds, you're going to lose some polynomial factor there, and it just doesn't play well with the errors.
Great, thank you very much. Let's thank Gal again. So next up, we have Dan Camon, who is from Starkware and is going to tell us about something called ECFFT Part 2.
Introduction. So I'm going to talk about how elliptic curves give us scalable and transparent proofs over all large fields. And this ECFFT is the brainchild of David Levitt from Starkware, and filling out the details has been joint work with myself and Elements of Son from Starkware and Swasti Kopati from University of Toronto. And as you see, it's ECFFT Part 2, and if you're interested in Part 1, that will be in 2 months in Soda. So the problem that motivates us is we have a very long computation that we want to prove the integrity of. And this computation has a succinct description. And we want 2 properties of this computation. One is transparent, so there's no trusted setup, as we heard in the talk 2 talks ago. And the second one is that it's scalable, so we have the prover time should be quasi-linear, and the verified time should be polylogarithmic in the length of the computation. It also depends on the length of the description, but we'll ignore that. And a solution that we have for this problem is stick proofs or Stark proofs. They're basically the same thing, just one has interactive oracle proofs and the other loses the interactivity. We'll focus on the interactive oracle proofs kind. But these have a big restriction, and that they require the fields be FFT friendly, which for the purpose of the talk will just mean that the multiplicative subgroup of these fields will have a large subgroup with order which is a power of 2. And we'll now dive into what these proofs are, and we'll see why this restriction exists. So, for example, we have this kind of computation, which is a recurrence formula, kind of Fibonacci-like, but it's not linear, so you can't skip ahead with some clever tricks. You have to do the computation step by step, and we want to do it for very many steps, 2 to the 40 steps, and we get the value, and we want to convince a verifier that this is what you get after so many steps without them having to do all of this computation themselves. So the first thing a prover will do is to interpolate a polynomial of degree 2 to the 40 that achieves exactly these values AI. And this polynomial will be evaluated on a cyclic subgroup of order 2 to the n of a multiplicative group, such that at g to the I, the value will be AI, where g is the generator of this subgroup. And after we interpolate this polynomial, we evaluate this polynomial on other cosets of this subgroup. So other sets of the form c times g to the I for all values of I. And the fact that we can interpolate and evaluate this polynomial on different subsets, this is exactly what we get from having an FFT. So we can do it in quasi-linear time. After we evaluate that, we want to show some things about this function. We have these 5 rational functions that depend on the function f, and we want to prove that all of these are low-degree polynomials. Why do we want to do that? We have 2 kinds of functions here. So the first 3 are boundary constraint polynomials. They just encapsulate the fact that that a0 is 1, a1 is 2, and an minus 1 is minus 1. So a1 is 2 if and only if f of g is 2, and that happens if and only if f of x minus 2 is divisible by x minus g. If it's not 2, then that quotient will be a rational function and not a polynomial, and it won't agree with any polynomial on enough values. So we will definitely get a contradiction. And the second set of functions are the constraints that encapsulate the recurrence relation. So if we plug in the second one, the first one of the long things, if we plug in g to the I for even values of I, then we get the term in the parentheses will be 0 exactly if the recurrence does satisfy that ai plus 2 is ai squared plus ai plus 1 squared. And that means that this thing will be 0 for x equals 1, g squared, g to the 4th, and so on up until g to the n minus 4, but not for g to the n minus 2, because a0 is not an minus 1 squared plus an minus 2 squared. So it should be divisible by a polynomial which vanishes at all of those points. And this polynomial, if we write it down, then it will have many, many coefficients. But it turns out there's a trick. It's very close to being the polynomial that vanishes at all even powers of gi, which is just x to the n half minus 1. So we just have to divide that polynomial by x minus g to the minus 2, and we get the correct vanishing polynomial. So we can just multiply by the inverse of that polynomial to get something that will be a polynomial if and only if the values of f actually satisfy that recursion. And we get the other parts of the recursion from the second function. So it will be true that if we convince verifier that all of these things are actually polynomials, then you must be convinced that the values of f actually correspond to this sequence. Of course, it's quite interesting to ask, well, how do we do that? But we'll get to that soon. And now highlighted are all of the parts where we actually use the FFT friendliness of this field. So the fact that there is such a subgroup for n equals 2 to the 40 is the FFT friendliness. We want it to be 2 to the 30 so that we will have the quasi-linear evaluation, interpolation and evaluation of the FFT. Even writing down these vanishing polynomials succinctly, it uses the properties of the subgroup, the fact that we can have this n half there, and for all other kinds of periodicity that we might have, uses the structure of the subgroup. And the algorithm that we use to prove this thing also relies on the FFT friendliness. So now let's dive into that algorithm, which is the Frye protocol, or randomly folded FFTs. So we want to show that some function from a given domain to the field is a polynomial of degree which is of less than the size of the domain. So for example, if the degree is 2n and the domain is 16n, we evaluated on 16 cosets, then rho will be 1/8 in this example. So the prover starts by writing down f as its even and odd parts. And we see that if we plug in x and minus x to this formula, then x squared is the same in both terms. And that means that we can get f0 of x squared and f1 of x squared from the values at x and minus x of f. Now, if we look at this set D prime, which is just all of the values of x squared for all of the x in the domains, we suppose that this is exactly of size half of D. So this means that the map x goes to x squared was exactly 2 to 1 from D to D prime. Or in other words, it means that D was comprised of pairs of x and minus x. They always have to come together. Now we compute some random linear combination of the even and the odd part, where the randomness comes from the verifier. And we provide oracle access to this function f prime on the domain D prime. And now what we want to show is that this is a polynomial of degree less than rho D prime. Because if f was degree 100, then the even and odd parts are going to be of degree 50 each. And then the linear combination is going also to be of degree 50. And it is actually true that if we can convince that a random linear combination is degree 50, then f0 and f1 must be degree 50 and f must be degree 100. And how do we show that it's this degree? Well, we just repeat the process because rho didn't change. We decreased both the block size and the degree of a polynomial by the same factor of 2. So if we just repeat this, eventually we will get to a very small domain. And then we just give a function. But what does it mean that we can repeat this? If we repeat this for 30 times, then eventually it means that not just the squaring map is 2 to 1, but raising to the power of 2 to the 30 is 2 to the 30 to 1, which means that we actually have 2 to the 30 of roots of unity in the field. And in fact, D must be a union of cosets of the subgroup of size 2 to the 30. And that again gives us, we must have FFT friendliness. And of course, it's not a coincidence because breaking down the function into these even and odd parts, that's exactly what the FFT does. But then the FFT will continue to work with each f0 and f1 separately. And here instead, we just fold them together and work with just one thing. So we don't blow up and we actually reduce the thing. So what can we do if the field is not FFT friendly? What we want is some other kind of algebraic structure, not the multiplicative group, but still has a large cyclic 2 subgroup. So we want it to be cyclic so that it can encapsulate some kind of iterative computation like the recurrence formula that we had. And we want the 2 subgroups so that it will have all of the substructures that we want and a fast transforms and so on. And we also need some analog of the squaring map, which is and the compositions of the functions that into the odd and even parts, which we need for FFTs and Fries in order for all of the things to work out similarly. And we can get all of these things from elliptic curves. So very briefly, what are elliptic curves? They're sets of points with 2 coordinates from the field that satisfy some cubic formula. It turns out that these things always come with some group structure on them, that you can add 2 points and get a third point. And what's very important is that this is not always just of size p-1, but they have sizes that can cover all the range from p-2 square root p to p plus 2 square root p. And in particular, there might be numbers that are divisible by large powers of 2 in that interval. So we get this very big theorem. By big, I mean it fills up the entire screen. That says that for any field, at least of size 7, we can find some elliptic curve that will have a large cyclic subgroup in it of size which is a power of 2, and it can go up to at least square root the size of a field in size. For special fields, it can be even higher than that, just depending on what power of 2 you can find in the material table that we saw. And in addition to having just the one curve, we also have a sequence of curves, as you can see down below, where we go from one curve to the next by a function, which is called a 2 isogeny, which act as homomorphisms on these groups, and they shrink down the cyclic subgroup by a factor of 2 each time. So we get smaller and smaller subgroups in every domain. And we also have these projections to the x coordinate from xy, we go to x. That's also a 2-to-1 map on curves that sends xy and x minus y to the same x coordinates. And when we just look at what these functions on top do to the x coordinate, we get rational functions of degree 2, which just look like x plus b over x. And these are also 2-to-1 maps on special sets that we get from these curves. And all of these things come together to help us with making similar constructions. So the x plus b over x, x in the place of x goes to x squared. So very briefly, there are a lot more details that go into this and a lot more subtleties. What do we get that we can use back for the sticks? So instead of evaluating polynomials of degree less than n, we have rational functions on the curve. So they the quotients of polynomials that depend on both x and y on the curve. And they're allowed to have at most simple poems at the points of the subgroup. So they can be evaluated anywhere else except for on that subgroup. And instead of evaluating on cosets of the group, we evaluate on sets of special sets, which are the union of 2 cosets of the subgroup of size 2 to the n, where we need both c and minus c, so that the projection to the x coordinate is exactly 2-to-1. That's the important part there. Instead of multiplying by g, when we computed f of gx, we just add the point g0, so it will be f of p plus g0 instead of f of p. And like multiplying by g preserved the degree of the polynomial here, adding the point g0 will keep the poles inside the same cyclic group, because that group is invariant to adding the point g0. So it will rotate the poles maybe in that group, but it won't send them to a different set. And instead of this decomposition that we had into the even and odd parts, we have 2 different kinds of decompositions. One is we have a function on the curve, we write it down as a sum of 2 functions just in the x variable, which have poles in a very specific set of points. And then each one of those, a function like that, we can write down as sums of 2 functions of lower degree with a lower degree denominator via the psi function. So first decomposition is along the projection to the x coordinate, and then all of the other decompositions are with the psi functions. And instead of vanishing polynomials, we will have some rational functions with appropriate zeros and poles. So here we also need to move the poles in a subtle way, because if we square or multiply some functions which have poles in g0 n plus 1, simple poles, then we will get double poles instead. And that's not of the same form, and we want to shift those double poles into simple poles on a larger subgroup. And as I said, there's a lot more that goes on in here, but unfortunately, there isn't enough time. Thank you for listening.
Thanks, Dan. Are there any questions? Yeah.
So do you know how practical will this construction be?
So it's not much more complex than regular stars. So it should be pretty practical, and in particular, more practical than implementing these prime fields inside other prime fields. We haven't completely implemented it yet, so we can't quite say, but the overhead doesn't look to be very large.
Let's thank the speaker again. So next up, we have Eduardo Siria Vasquez, who is going to tell us about interactive proofs of infinite and non-commutative rings. Take it away.
Thank you very much. Hi, everyone. So yeah, this talk is about interactive proofs. The previous one was about getting things to work over many fields. Now this is about getting things to work over many rings. So I expect everyone in the room to know what's an interactive proof, but maybe the term doubly efficient is not on top of everyone's head. So with doubly efficient interactive proofs, I'm referring to like these GKR style proofs. And you know, so in particular, we have the prover to be efficient. And furthermore, I'm going to abuse a little bit that name. And whenever I talk about a doubly efficient interactive proof, I'm going to refer to a proof where the prover is linear in the size of the circuit as the state of the art. And the verifier, yeah, is quasi-linear in input size and logarithmic in the circuit size. So what's good about interactive proofs, right, is that then we can go and tell people, oh, we're solving a practical problem. We're solving a verifiable computation problem, and give us funding, please. Oops, sorry. So we have the verifier and the prover. The verifier has some circuit and some input X, and maybe the verifier is too lazy or doesn't have enough resources. So what the verifier does is that it's going to ask the prover to compute on the input and return the result with some proof. And this is not quite there for practice because people care about programs more than they care about circuits. And you know, like there's really, really efficient work here, but you can't forget the whole picture, right? So whenever anyone wants to deal with a problem like this, and you have some program, you have these kind of two steps. First, you have some sort of compilation from your program down to the arithmetic circuit, and then you feed that to the backend, right? That's works over circuits. And one thing I want to argue about in this talk is that, you know, it's important to remember this connection. So the fact that the backend is limited to finite fields is a limitation for the front end because it's going to be more complicated. You have to compile from your program down to finite fields. Okay. So as I said, yeah, usually the backend only works over finite fields. There's one exception I want to mention. There's this paper by Chen Cheong, Kim, and Park, where they generalize GKR to work over finite commutative rings. Somehow not accepted anywhere. And in this work, what we do is that we extend this to work over rings that can be infinite or can be non-commutative. So as the ones you can see in the slide, but pretty much a lot of them. We preserve the complexity of the state of the art when you have like a finite field here on the back end. And furthermore, in some cases, we get a prover that is sublinear in the size of the circuit for some specific rings. So this works, for example, with matrices and polynomial rings. That was already known using different techniques. But we can also make, you know, I'm not aware that this was known, for example, for certain Clifford algebras, that we get like a sublinear prover in the circuit size. Okay, so that's on the one hand. And another kind of preaching I want to do in this talk is about how real numbers are different from floating point numbers. So we know that, but let me get into some details, right? The fact that no previous work supported infinite rings meant that you couldn't do exact arithmetic. So you had to resort to approximate arithmetic and use, yeah, floating points or something like this. And one problem with approximate arithmetic is that it's not very algebraic. You don't get a ring. So you don't get something that is associative, or you don't get something that is distributive. So the first problem with this is about efficiency, right? When you kind of compile down from your program down to a circuit, now you're going to have a bunch of gates to emulate the behavior of like, you know, like approximate multiplication and approximate addition. Another problem is that, you know, people are like, oh, but it's fine. Also, like, it's not so different to do floating point or to do exact arithmetic. So here I have one example about, this is like a logistic map. What you can see in blue is the, what's the term xn? So that's the n axis. When you do exact arithmetic. In red, you cannot really see it, but that's what you get when you do approximate arithmetic using double precision floating point numbers. And the important bit is what you can see in black. This is the difference between both of them. So, the relative error here is pretty big, and also the behavior is not quite easy to deal with. Okay, I take that that's because of a logistic map about the behavior, but it's what I want to say is that it has some problems using floating point arithmetic or approximate arithmetic. And this is like even in the best case scenario, right? We all know how to implement this circuit, very simple. I'm just going to do this to change these products. But now let's get back to the problem of compiling programs down to circuits. Since approximate arithmetic is not a ring, and it's not associative and not distributive, whenever I go from a program down to an arithmetic circuit, the wiring in this circuit is going to bias the output. So whether I do like, how do I order my multiplications, or whether I do like, this kind of operation or that kind of operation, that's going to affect the result. So now this is like some sort of attack vector in your broader system, and we should be aware of this. Okay, so that's preaching for exact computation. And a small recap of the contributions is that, yeah, now we have a backend, double efficient interactive proof that works over any ring, and I will get to the details of any in the next slides. This is theoretically interesting because we are now more aware of what kind of algebraic structure do we need to build like GKR style kind of proofs. It's also nice that we discover like new rings with sublinear provers. In practice, this is also interesting because when you have like a very flexible backend, you get like a very flexible front end, right? If I, for example, have some problem in robotics and I need to use quaternions, now I can simply like compile to a circuit over the quaternions, and I can reuse software, and in practice these things matter. And yeah, as I said, now we can do exact computation, which was impossible before and has some pitfalls doing approximate. Cool. Okay, so I'm going to tell you a little bit about the technical details. And I'm just going to like any outsider of the field could understand this, right? Like in order to get the soundness of these protocols, at some point you need to reason about the number of roots of a polynomial. So how do you do this proof usually, right? So, okay, we have some set A, we have some polynomial of degree D, and we want to prove that F has at most D roots over the set A. So the way you do this proof over a field usually goes by induction on the degree of the polynomial. And at some point during the proof, you take a couple of roots in A, and then you say, okay, I'm going to express f of x as the product of q of x, where q is of degree d minus 1, times x minus 1 of the roots. Now I'm going to evaluate f over the other root, a2, so that's 0. And now I know, okay, that means that q of a2 times a2 minus a1 is 0, which in turn implies that a2 has to be a root of q. Q is of degree at most d minus 1, and then you use your induction hypothesis, and you're done with the proof. So this is how it goes over a finite field. And I want to like kind of highlight some properties that we are using here that maybe go under the radar. First of all, we have Euclidean division for polynomials. Second, we're using the fact that evaluating polynomial evaluation is a ring homomorphism. So here, like, the evaluation of the product is equal to, yeah, the evaluation of f at A is equal to the evaluation of this product. And we're also using the fact that this difference here is not a zero divisor. So this has to hold for every pair of elements in this set. Okay, so forget about the proof. Let's remember what we need for the proof to go through. This property here, that the difference of the points is not a zero divisor, this is just an assumption we will have to make on the set. So people call this like exceptional sets or regular difference sets. And the other two properties, they follow easily if this set A is contained in the center of the ring. But if we relax the requirements on A, so that the elements of A just commute with each other rather than with the whole ring, things get really hard. And some example rings where it's interesting to do this relaxation is like matrices rings. So we care quite a lot about those rings. So yeah, again, like no time to give details, but just like a very rough sketch. The solution to deal with this is that I'm defining like a new polynomial ring. where the core idea is that indeterminate X is going to commute with wherever the set A commutes. And this is not something that was in the literature. I was trying to look for something like this, and I had to build this from scratch and reproof a lot of like basic algebra. And actually, even if you have this, I wasn't able to bound the roots in this set for all the polynomials in here. So just some particular subset of those, and again, the specific subset we can talk afterwards, or you can see the paper. And since it's only this kind of subset of polynomials, that also requires modifying the layer consistency equation in GKR when you go like from one level to the previous one, and to also modify the sum check protocol so that all the polynomials that you encounter when you proceed in the protocol are in this specific subset of polynomials. And once you have that, of course, I wanted to have like a linear time prover, so you also need to like rework all of these algorithms that you have in the Libra paper to get like a linear time prover. So that's like a good amount of that's the bulk of the paper. So yeah, as a recap, what we get, this is like the one slide with the result. Given some ring that is possibly infinite and possibly non-commutative, as long as it contains a set which is commutative, which means that the elements of the set commute with each other, and which is regular difference, which means that if you take the difference of any two of them, it's going to be in, a regular element. You can do GKR over that circuit. And the reasons why these are interesting is the ones that I mentioned before. So it's theoretically interesting. We know, what are the algebraic barriers to do like these kind of protocols. We get sublinear provers for new rings, and like a different way to get sublinear provers for other rings that we knew about, like matrix rings and polynomial rings. It's interesting in practice because black box is not only theoretically interesting, it's also interesting for like having agile software. And we're also able to do exact computation. So, approximate computation is great, but, be aware of the pros and cons of exact arithmetic and approximate arithmetic. So, yeah, thank you very much.
Thanks, Eduardo. Are there any questions?
So thanks for the talk. I just wanted to ask, like, the focus of the talk, the paper is like on double efficient proofs. So how do you deal with infinite ring, or especially like with real, maybe ring, like with the field of real number, like which are probably hard to represent and take too much space or time to compute. So how do you address these issues? Like, thanks.
Yeah, so kind of at the paper level, this is not a concern, right? I say like, okay, give me an infinite ring, I deal with it. In practice, yeah, like you cannot represent something infinite quite easily, right, on a finite thing. So there's this whole, so there's several things you can do. If you, as long as the input has like finite length, you can compute your circuit, and okay, the size of your data is going to grow like with the depth of the circuit. And other thing that you could do is that, we can deal with these things even with pen and paper, right? What's pi? It's pi, and what's the square root of pi square? It is pi. That's not, of course, like exact arithmetic is always going to be less efficient than approximate arithmetic, but we're aware of this, but we also should be aware of the limitations of approximate arithmetic. And this is why I was bringing those up. And, when you have a scenario where, who decides the compiler, right? That becomes like a new kind of problem. So, yeah.
Thanks. Any more questions? Yeah, so I guess this talking about exact arithmetic. So does this mean that you can sort of do proofs with like symbolic computation?
Yeah,
and things like that? That's very cool. Right. Okay. Then let's thank Eduardo again.
Hi, everyone. I'm
Oh,
Rachit Garg.
excuse me.
And oh, sorry.
So next up, we have Ratchet Garg, who is very keen to give his talk. So
Yeah. Hi, everyone. And this is joint work with Kristen Sheridan, Brent Waters, and David Wu at UT Austin. And the title of the talk is slightly different from the title of our paper, where I'm going to talk about fully succinct and updatable batch arguments for NP from indistinguishability obfuscation. Let's begin with what are batch arguments. So imagine you have a prover and a verifier, and the prover wants to convince that a circuit C and a sequence of statements x1 to xg are all circuit satisfiable. So what I mean is that for each of these statements, there exists a witness, such that when you run the circuit on the statement and the witness, you get 1. So what a natural proof strategy is, the prover can send over these witnesses to the verifier. The verifier can run the circuit and output 0 or 1 if all these witnesses are circuit satisfiable. So this is a fine proof strategy, but in general, we care about the size of these proofs that we send over to the verifier. And we are going to be in this common reference string model where both the prover and the verifier share this common reference string in the sky. So what is the size requirements on our proof? There's going to be 2 requirements, one on the number of instances and one on the circuit size. So if the number of instances that you're batching for these batch arguments or barks, if it's sublinear in the number of instances, we say it's non-trivial, but we can ask for more succinct proofs where we have a polylogarithmic in the number of instances proof size. Similarly, for circuits, it can either be polynomial in the circuit size or polylogarithmic in the circuit size. In this talk, we'll focus on fully succinct proofs, where the proof size will be polylogarithmic in both the number of instances and the circuit size. So we require 2 properties from such a barg. We need completeness, which says that an honest verifier, an honest prover who knows the witness can convince the verifier of true statements. Soundness says that no efficient prover can convince an honest verifier of false statements. So great. Let me go with some prior works. So to construct these fully succinct bargs, what you can do is you can use succinct non-interactive arguments for NP. But the caveat for using succinct non-interactive arguments are that there's a long line of work, and these existing constructions are either in the idealized models, which means random oracle model or the algebraic group model, or use strong knowledge assumptions. There's a construction using indistinguishability obfuscation and one-way functions, construction from Sahai and Waters from 2014. But the caveat in their construction is that the CRS size grows with the number of grows with T, where T is the number of instances that you're batching. So if you generate a CRS up front, you can only support a priori fixed number of instances to batch. In this talk, we want to support an arbitrary polynomial number of instances to batch. And there are other constructions of bargs, but they're not fully succinct from different group assumptions or different algebraic assumptions. Okay, so let me focus on our results. We construct a barg for NP, which can support arbitrary polynomial instances to batch. We get proof size, which is lambda times log T, where T is the number of instances, and this is fully succinct. And I want to remark that you can combine some existing constructions, such as the Sahai Waters 2014 SNARG and a construction from Chaudhary, Jain, and Jain in 2021. But an additional part of our result is that we also get some nice properties about these proofs. In particular, we can have updatability in our proofs, which I'll mention in the next slide. And there are constructions which do updatability in a recent work, but they're not fully succinct. So the high-level view is that we get a more direct construction, similar to the Sahai Waters 2014 construction from IO and one-way function, and it avoids the Fiat-Shamir correlation intractability framework. So what are these? What's this updatability property I'm talking about? So imagine you have a prover, and we are in this common reference string model, and a prover generates a bunch of these proofs by batching these sequence of statements. So it has statements x1 to xg, and it batches it to a short proof pi1. It has similarly polynomial number of these batching instances, and it's batched all of these proofs together to these short proofs, pi1, pi2, and pi t dash. For the updatability property, we require that just by looking at these proofs, the prover can aggregate these proofs together to a very short proof pi. So imagine if you knew all the witnesses up front, so then you can run a regular batch argument and create the short proof pi. But here we ask that looking just at these proofs and not remembering these individual witnesses, you can batch all these proofs pi. And we want full succinctness, which is polynomial in the lambda and logarithmic in the number of instances and the circuit size. And an additional thing we want to support is we want to support polynomially many, arbitrary polynomially many updates. So you can do some snark composition techniques to get constant number of updates, but we want to get arbitrary polynomially many updates support. We want to support arbitrary polynomial updates. So that's great. We have these nice properties that we want out of our scheme. So how do we, what do we use to construct it? So I'm going to use a 2-to-1 hash function, which is basically, it hashes 2 inputs each of L bits to something which is approximately L bits. There's going to be some statistical property, which I'll mention towards the end of the talk when I'm talking about the proof. For now, we can ignore that property. Our second ingredient will be indistinguishably obfuscation and one-way functions. So let me go through the snark for NP construction from 2014 by Sahai and Waters. Informally, their construction in the CRS, you publish 2 programs, a proof program and a verify program. The proof program takes in a circuit C, statement X and witness W. It checks if the statement and the witness verify, or the circuit outputs 1, and it outputs a MAC on the circuit and the statement. The verify program just simply takes the MAC and the circuit and the statement and checks if the MAC verifies, and it outputs 1 if it verifies. Of course, you don't want to publish these CRSs in the clear, these programs in the clear in the CRS. So I'm going to do some sort of obfuscation of these programs and publish that. So notice that if the proof size here depends on the size of this MAC. And if the size of the MAC is security parameter many bits, we get a proof size which is security parameter many bits. But this does not support arbitrary polynomially many instances. The reason for that is the CRS will grow with the number of statements that you want to batch together. So imagine if you have too many statements, your proof program will now check each of these statements. It will run circuit on each of these statements and each of these witnesses. So the CRS will grow with the number of instances T. And it's not clear how to update these proof, arbitrary polynomially many of these updates. Okay, so our contribution, we'll create this 2-to-1 proof merger program. So below, these are these 2 Sahai Waters programs, prove and verify. And additionally, we're going to create another program, proof merge. What this program basically does is, imagine you have a left node and some hash function, some hash value. It verifies MAC on this left node. It verifies MAC on this right node. And it's going to hash using your 2-to-1 hash function. And then it's going to, if all of these verification steps are correct, it's going to output the MAC pi on this merged node, which we'll call parent node. Okay, so we have this program in our CRS, and the proof size still remains lambda bits, which is the size of the MAC. And there's no dependence on the number of instances in the CRS. So at the surface, it seems like you can support arbitrary polynomially many polynomially many instances. So let me show you how, using this technique, you can do updates. So the basic idea is using Merkle hashing. And imagine you have a statement X and a witness W1. You're going to use your proof program to create a short proof pi. This is the original proof program from Sahai Waters. So now when you get another statement X2 and a witness W2, you can again run the proof program and get a short proof pi. But now you have 2 trees of height 1. So you can merge these 2 together to create, first using a hash value using the SSP, using the hash function. And then using the proof merge program, you can merge these 2 proofs together, pi1 and pi2, to a short proof pi1, 2. And once you've merged these proofs together, you can forget all the intermediate nodes. Similarly, you can do this when you get X3 and X4. And then you can merge these together to a tree of height 2. And now you have 2 trees of height 2, so you can again merge them together to a tree of height 3. So this is how you basically perform updates. So great. Let me briefly go through the security proof. So in the security proof, we're going to focus on the non-adaptive soundness, where there's an adversary and the challenger. The adversary sends this circuit and the sequence of statement that it wants to challenge on upfront. The challenger generates a CRS, and then the adversary outputs a bad proof file. So in our security game, basically, we are going to change the proof program so that on some of these XI, when XI is an instance which is not circuit satisfiable, I'll always output bot. Since XI was a statement which was not circuit satisfiable, notice that these two proof programs are always same on all inputs. So we can use IO security to argue between these. A very high level view of our proof structure is then going to be, imagine X1 was the bad instance, and you change your proof program to output no proofs on statement X1. The main technical challenge, which is going to be referred to the paper, is going to be to how to move these proofs tree by tree in a structure where there's no proof for this hash statement H1, 2, then there's no proof for this hash statement H1, 2, 3, 4. Once you move all the proofs up, the verifier will always reject on this challenge statement. So to conclude, we construct a bar for NP from IO, which is fully succinct. We have this nice updatability property, and it's a direct construction from IO in one-way function. In our full paper, we do talk about adaptive soundness, and we use complexity leveraging for our techniques. But the caveat is that we can still do proofs, arbitrary many updates, but the caveat is the proof size is no longer fully succinct. So, and another nice property that we get for free is zero knowledge of our construction. So, thank you.
Thanks, Richard. Any questions? Yeah. In the middle.
So thanks for the talk. So if we replace the CRS in the Sahaya Waters construction to work with IO for Turing machines, does the CRS size still grow with the number of instances?
No, it still depends on the number of inputs you take in. Like your program still takes in X1, X2, X3. So even if you replace it with the Turing machine, the CRS grows still with the input size.
Okay, thanks.
So for when you update the proofs, do you prove adaptive soundness for updated proofs, or is soundness defined only for single shot proofs? Do you have like adaptively sound multi-shot updatable proofs? Do you have like a definition like that, or is it just adaptive soundness for one shot proofs?
So you mean that if you have, we can prove something stronger where you mean that if the original proof verifies and then you want to output an updated proof. But for the soundness definition,
I mean, an attacker provides you a proof that can be an updated proof, and basically gets a CRS, then it finally gives you a proof, and that is not technically a proof that was created using just the proof algorithm, or just hypothetically, because there's like a single verifier that takes us input.
Yeah, our definition will account for
okay,
that.
Yeah. Gets adaptive soundness even for that.
Yeah.
Okay, thank you.
Okay, so let's thank Richard and all the session speakers again.